Hello everybody! I hope you're having a beautiful day. I want to welcome you on to the stream today where we're going to be doing a special talk, lesson, lecture, whatever you'd like to call it. My name is Dr. Daniel Page, but you can just call me Daniel or Dan. But specifically today, I will be the estate manager of a haunted house with this very bizarre floor plan behind me. I totally would like to trust me at the moment, but here's the problem. I've decided, because you wanted to come see the house, I plopped you in a room in the house, say right about here. And here, let's see here. So this is where you are right now. Yeah, we're on that weird side of the internet all of a sudden. So there's you. You're the traveler. And the thing is I don't really have as many treats or snacks for everybody. And you're like, hey, look, I just want to get out of this house. Then there might be a lot of spooky skeletons and spooky ghosts coming out to get you. So we would need to get out of here, especially if I have any plans on top of this. With my low budget, I've also placed traps to stop you from escaping from my poor quality appetizers, to prevent you from escaping, to slow you down from getting to that exit, okay? Now, I assure you that you're smart enough to know not to get trapped by my traps, because like I said, they're really low budget. So I gotta tell you a little bit about how this haunted house is like, so that you can get a flavor for this. So we'll talk a little bit more about the problem formulation and go there when we get there, okay? So I just want to lay out the scenario for you. So right now, you're in this room, for example. Keep in mind that this layout can be as magical as you like. Just as magical as, say, I don't know, the way I look at the moment. Truly magical. Truly magical. So keep in mind, that's just one example of how my haunted house can be configured. So the thing is, you start in this room. Here's the appetizers. Let me draw some. Let me just put some appetizers out. We got a little table here. Let's put some crackers. Yeah, those are crackers, by the way. I'm going to indicate that those are crackers. Don't mind my writing. It looks like it's melted through a fridge here. And then I got some cheese over here. Some crackers and cheese. But I'm just saying I got some of the more stranger, more exotic tasting cheeses that you may only want one and never more. So anyways, in this haunted house, we have some stairs here. This isn't terribly long to get to this house, to this room here. So I've indicated the rooms with these rectangles. And there's passageways that go between the different rooms. So for example, I got some stairs that bring me up here. There's also this other passage here called the jelly passage. The walls are made out of jello, okay? I can't trust or assure you that there's anything strange in this passage that isn't squishy, okay? So let your imagination use that however you like. So you can go to, for example, to the jelly passage to get to the teleporter room. Now there's this very special room called the teleporter room. Not every haunted house is going to have one of these, but in this particular one, this haunted house has a teleporter room that allows you to teleport right to the exit room. Now, it doesn't have to have one of these, like I said. This is just my configuration for my haunted house. Like I said, I have interesting tastes. So, likewise, I could go instead through the spooky passage. And the spooky passage, of course, has lots and lots of ghosts. They hang out with me on Saturdays. So, you can get to this room. This room, for example, has some stairs that come in and out. One of them takes you to the teleporter room. And we're getting some weird noises on my end. But anyways, I'm just hearing the ghosts, okay? So I got some stairs here. And of course, I have the teleporter room. There's this other room. Now, to get to this room, you could either come from the stairs, you can either come from this place called the Maze of Doom. It's so complicated, I haven't even drawn it for you, but it takes quite a lengthy time to get through the Maze of Doom to the exit room. But there's also this fast track. It's literally a choo-choo train that goes through my haunted house, that goes from here to there. I didn't tell you, though, that the train runs on D-cell batteries. So keep in mind, it is fast, but low budget. Just try to use your imagination. And of course, I mentioned the maze of doom. This is one way you can go from this room to get to the exit room, or from this room to get to the exit room. But like I said, it's quite a lengthy trip to go through there. I once left my laundry in there, and I didn't find it for a couple of weeks. So anyways, this is the layout for the haunted house here in our example. Keep in mind, this is just one example. In fact, like I said, the teleporter room is just another way to go from one room to another room. So it's nothing particularly special about the teleporter room. Let's just ignore the physics about it. Let's just assume that it's just, I go from this room to this room. My point is that there isn't really a geometric interpretation of this map, okay? There's a little bit of a magic spookiness in this. So anyways, I gotta tell you a little bit about this. So here's the thing. I'm not entirely cruel when I put my potential customers, these travelers, in here. I'm gonna give you a map. So you're gonna have a map of an ever bizarre design. So you get a map. So you know where all these rooms are laid out, like this. You're also going to get a measuring device. And it's going to be made of magic, okay? Like I mentioned, this configuration of this haunted house isn't terribly, it doesn't follow what you would think. When you literally look at this, you would think, okay, the teleporter room is quite lengthy away from here, but we know a teleporter can take me there really fast, right? Likewise, the Maze of Doom, literally, I didn't even draw how long this is, right? So keep in mind that this measuring device, it allows me to know how far away one room is from another, and I can use this measuring device to figure out potentially the shortest way to go from this room to the exit room. So just keep that in mind. And of course, you know where you started. So where the traveler starts and where the exit is. But there's a catch, and I brought this up. I brought up my low budget traps, okay? So I brought that up. I'm gonna need an assistant to help me with this, wherever she went. I got Miss Kitty. Here we are. So I got Miss Kitty here. Everybody say hello to Miss Kitty. So, anyways, I gotta tell you the rules. Miss Kitty, you're knocking the flames right out of my passages. Why are you doing that? So Miss Kitty, imagine Miss Kitty is you, the traveler. And suppose you run across one of my traps. Now, keep in mind, I didn't mark on the map where the traps are, but I told you that there's at most K of them. So I'm very dramatic like that. I'll tell you, well, I didn't tell you where the traps are, but there's at most K of them. But here's the catch. The only way you're going to find out about where these traps are is if you get close enough to one of them. So here's Miss Kitty. She gets over here. Now, keep in mind, if this edge, this passageway is safe to go through, Miss Kitty can go past here, right? She can go across like that. However, if she comes across an adjacent room to a trap, Miss Kitty is cunning like you, like we established. You're smart enough not to get caught by one of these traps. What happens is the trap gets sprung, and you can't go any further. So Miss Kitty can't go this way anymore. So we have to reroute our travel somewhere else, like over this way, or perhaps over back this way. Miss Kitty's gonna moonwalk, okay? Like this. But anyways, thank you, Miss Kitty. But here's the thing. So there is an element to this, is that you don't know where my traps are. You don't know where these traps are. These guys. And the thing is, you won't know until you've come across them. But you're cunning enough to know when a trap is coming, okay? Because you're smart enough not to get into my low-budget traps. Like I said, I'm not kidding. This is a low-budget trap. It's literally attached together with a straw, okay? So anyways, does everybody understand the rules here? So So you are looking for a way out of this my haunted house, and there's these traps. You don't know where they are. And the catch is that I don't know where the traps are, but they only spring when I'm close enough to them, okay? So there is at most K traps. They are discovered upon entering a room beside a passage with a trap. And of course, you're going to be cautious. You're not going to run right into that pit. You never know what could be at the bottom of it. So just be mindful of that. So does everybody understand the rules of how you can escape this haunted house, okay? My low budget haunted house. So you can escape it, but here's the thing. You really, really want to get home to watch your favorite television show or watch something on YouTube other than this. So you want to get out of here as fast as possible. Miss Kitty, you coming to hang on out? Okay, you can hang on out. As long as you behave yourself, okay? So, anyways, now you look at this really complicated map. Like I told you, it's like magic, right? But here's the thing. I have a measuring device. And here's the thing. Sure, this looks really complicated, but there might be a simpler way of representing this. So I'm going to show you how you can represent this using something we call a graph, which I'm going to introduce some terminology for you. And then I'll formalize our problem, and then we'll see what we can do to escape the haunted house. Miss Kitty, you're being very silly at the moment. So what I'm going to do before we get into like anything too fancy-pantsy, because I want to keep it rather concise and easy for you to understand, is you look at this and you have a whole bunch of rooms, right? What I'm going to do is I'm going to represent these using what we're going to call a weighted graph. And I'll define what that is in a moment. But you have all these rooms and they're connected via some passage. And I have a measuring device that tells me how to go from one room to another, right? So that's what I'm going to do is I'm going to simplify this down a little bit more. So what I'm going to do is I'm going to designate where I've started, where the cheese and crackers are. I'm going to call this vertex S. So that's going to be the name of these circles. Sometimes people call them nodes. I'm going to call them vertex for singular, vertices for plural, okay? They're otherwise, like I said, node versus nodes. Nodes is plural. So I'm going to take each one of those rooms, and I'm going to number them except for the exit room. The exit room, I'm going to call that T. And I'm going to have a whole bunch of these rooms here. So I'm going to call the one right by the stairs and the fast track and the maze of doom over there. I'm going to call that vertex 1. I'm going to call the one with the teleporter room is going to be room number 2. The one near the maze of doom fast track and the stairs over there, that's going to be vertex 3. And the one near the bottom, that's by the spooky passage, that's vertex 4. So notice everywhere I have a passage, I'm going to draw a line. Keep in mind, it doesn't have to be a straight line. It could be a curve. It just represents the connections between our dots, the vertices, and what we're going to refer to these passages as are edges. So let's fill this in. So I'm just going to draw lines. Where exactly? So for example, I have a room from the cheese and crackers to up the stairs. That brings me to vertex 1. The fast track takes me down to vertex 3. The stairs here take me down to vertex 4, and the stairs here take me to teleporter room. I have the maze of doom. Now keep in mind, the maze of doom actually isn't a room. It's a whole bunch of passages. But the point is it takes me, it could go from through the maze of doom to get me to the exit room. It could be that that I could take the maze of doom to get to the exit, right? So this maze of doom, I'm going to model it like this. So let's see. I think I got all the connections, right? Oh, we forgot the teleporter room. So like I said, they don't have to be straight lines or anything. I can just draw it like that. So they just represent the connections. So these things here, these circles, like I said, this is a vertex. Plural is vertices. And these lines that I have here, or curves, these are what we call edges. They represent the connections between the vertices. So in this case, if I call this a graph, so this would be graph G, and it has vertices, which are going to be capital V. So that would have S, 1, 2, 3, 4, and T. Those are the vertices. They'll be in this set. We have to bring up the dreaded M word, the mayonnaise. And the edges, these are going to contain all of the pairs. These pairs of the, what we call endpoints of an edge. The endpoints are simply the vertices that are on each edge. So notice that if I look at this edge here, the ends of it are 4 and 3, so those are what we call the endpoints. That's how we represent the edges. So I'm not going to go too detailed into that, but the point is Miss Kitty, why are you attacking me? So I know you want out of the haunted house, okay? So let's see. So now you can see I can represent this much more complicated thing much easier over there. But I only got the connections. What am I missing? What did I mention about the, I want to get the fastest way out. What do I need to do still with the connections between the rooms and the passages? There's something I'm missing that I need to do. I need to measure. I need to know. So I have to look at my map, and I have my magic measuring device. And I should be able to go to each one of these, and I could go on my map, and I can measure out how long each one of these is. And keep in mind, like I said, it does not have to abide geometric rules, okay? Miss Kitty is going bonkers here. So, Miss Kitty, why are you attacking me? I know you really want, and you're laying in the trap. Anyways, Miss Kitty, you're getting me really in trouble here. So, anyways, I wanted to find what an undirected graph is. Before that, I want to measure these out here for us. She is trapped. Yeah, exactly. She wants out of the trap. Look at this. She's like, I just want out of here. Save me. She's been defeated. So, suppose I take my measuring device and I measure these out. So suppose that these are the measurements I get. I get 1, 6, 7, 1, 1. So like teleporter room, makes sense that it's like 1. So this is like how long it might take me, or the cost, or the length, of how long it takes me to go from one room to the other room. 9 and 8. Like I said, the Maze of Doom is really long, right? So this is an example of what we call a weighted graph. So a graph consists of vertices and edges, and a weighted graph will have it where all of the edges have a number associated with them. For us, we don't care as long as it's some non-negative number. That means it's 0 or greater, so a 0 or positive. And Miss Kitty, are you ready? We got to talk about some tools we're going to need here. So one thing I haven't mentioned so much is what a weighted graph is, specifically based on that definition over there. So a weighted graph is simply where we associate each one of the edges with some number. So I have a number at each one of the edges. They represent, say, the weight of that edge, hence why we call it a weighted graph. So these numbers could represent lengths. They could represent a cost. In terms of the graph theory, it doesn't make any difference. So you can have costs on the vertices, costs on the edges. We're going to only care about when they're on the edges, okay? That's all we need for this problem. So I'm just going to make some formal notation here. So if ever I want to get the length of a path, length of the path, all I'm going to do is, so imagine I took from S to T and I go S, 1, 3, T. I add up the edge weights on them because that's the cost it takes me to go from S to T along this path. So I got 1, 2, so that's a 3 so far, plus 9, that's 12, right? So that would be the length of that path. So the length of the path, I'm going to denote this as d of p, where that's a path. So it's just the sum. So this is just simply the sum of the edge weights along the path. So hopefully that's clear. So there's one important detail now that I could define for you, is the idea of a shortest path, right? So now that I have a definition for a length of a path, how I can measure it, I want to know what exactly is a shortest path. Does anybody have any ideas what a shortest path would mean? So as the name suggests, I'm going to look for what is called so in our case, we want to go from the room we started at to the exit. So we would like to compute a shortest ST path. So that's what we're going to look for. So I call it an ST path because it describes the ends of the path. Miss Kitty's had enough of this. So, anyways, so we're going to look for one of these. Now I have a question for you. If I knew where all the edges were, or perhaps there was no traps at all in the haunted house, does anyone have any ideas of how I could compute for my traveler? So I want to take my traveler from the start to the exit. Can somebody tell me, how can I compute the shortest way out of here? I compute a shortest ST path. Yeah, there is an algorithm that's really nice for this. You can use what is called Dijkstra's algorithm to do this. So if there's no traps, you could just use Dijkstra's algorithm, which I'm going to outline now because it's going to be relevant for us. So if there's no traps, you could just use Dijkstra's algorithm. And I'm going to describe it to you more like we just apply it. If you want a more formal adventure into this, actually I recently did a series of lesson videos actually relating to Dijkstra's algorithm on the YouTube channel. So you're welcome to check that out. But I'm going to just cover what we need to know how to compute a shortest path for, say, for example, right here. So what I'm going to do is I'm going to start off by giving you the idea here. So I'm going to distill it down to something that's easy enough for you to apply if you needed to just quickly compute a shortest path, okay? We're not going to go fancy-pantsy with it. Like I said, I have a whole lesson series on this algorithm, this Dijkstra's algorithm, on the channel. So let me show you how you could do this. And so I'm going to give you the essence of Dijkstra's, okay? So Dijkstra's algorithm here. For those that are wondering why it's called that, it's because it's named after the pioneering computer scientist Dijkstra. He's Dutch. So what can I say? Anyways, here's how it's going to work. So let me just get my lovely markers out. So what you're going to do is you're going to imagine that there's vertices in this graph that either could be in a blob or not in a blob. And I literally mean like a blob that goes around devouring everything, okay? So you're going to imagine this blob starts off where you are, S. So you're going to conceptually imagine this blob, and the blob always is going to follow this rule. Miss Kitty, you're being silly. She's in the trap too. She's just enjoying this. So here's the rule in Dijkstra's algorithm. You're going to always pick the closest, well, I'll say the next closest vertex, not in the blob. That's all we're going to do. So we're going to imagine we measure out how far away we are from the source, S, where we start. And I'm going to try to find the next closest vertex that's not a part of this blob yet. And when it does, the blob is going to devour that vertex, and the edge that I use to go across to get to that vertex is going to consist of me extending some shortest path from this vertex to some other vertex. And we can stop this process when we reach T, for example, but you can continue this process and produce something called a shortest path tree, which, again, I spent a lot of time discussing this at another lesson. So let's do an example of this so you can see how you can do this, and it's really not that hard. So watch this. So notice that if I want to compute the next closest vertex not in the blob, remember the blob right now is just devoured S here. Which vertex is closest to S? Well, we got 1, 2, or 4. So we got 1 versus 6 versus 7. Which vertex should the blob devour next? So which one? Miss Kitty is trying to figure this out too, okay? She's learning. We want vertex 1, right? Need vertex 1, yeah. So what the blob is going to do is going to extend out and devour vertex 1 and uses this edge to get there. So now we just apply this rule again. We find the next closest vertex not in the blob. Okay, well look, notice that to get to T is 1 plus 8, that's too far, right? 1 plus 2 is 3. 6 versus 7. Looks like vertex 3 is next, right? So all I'm going to do is I'm going to let the blob devour vertex 3. And it's going to use this edge. And then next, we've got ourselves, what's the shortest, the next closest vertex that's not in the blob? Okay, we've got 4, which is, now look at this. You see it's 1 plus 2 plus 1, which is 4, right? That's just 4. Versus now we've got, so now we got 4 to get to here. We've got 6 to get to there. We've got at least 9, right? It looks like 4 is going next, okay? So the blob's going to swing around and devour vertex 4 next. So it goes around, swings around, and devours vertex 4 via this edge. And then next, which one is the next closest vertex not in the blob? So all you do is you're trying to figure out which vertex is closest to the blob's source, where the blob landed. So we've got now notice that my choices are, well, they're quite limited now. Notice that now I've discovered this edge here with weight 1. So I got 1 plus 2 plus 4 plus 5, right? So I got 5. So I could go 5, or I can go, let's see. So the next closest one is, it looks like we got T or 2. Which one is going next, T or 2? Miss Kitty, do you know? Do you know which one it is? She says it's vertex 2. So let's go with vertex 2. So the blob devours vertex 2, and it's via this edge. And then finally, there's vertex T over here. Well, what's the least weight edge that takes me there? Now we have 9 versus 10, at least 10. So we got 3, 9, that's 12, right? Then we have, okay, now we know that we get there with a total distance of 1 plus 2, it's 3. We got 4, 5, so we got 6 versus 9. So it looks like we're going to devour T. Well, the blob is, to be more specific. I'm not the blob. I am the residence manager. I am the manager of the estate. I have a lot of different titles, okay? But intuitively, it makes sense that you would try to use this teleporter room, right? So that means that if you actually look at this, let me just highlight the shortest path. Yeah, exactly. Now, very good, everybody. So now here's the shortest path right here. This red marker is being a little bit weird. So notice all I do is I go from S, 1, 3, 4, 2, and then I take the teleporter room all the way back over here to t. And that's how we can compute the shortest path. So just remember, when it comes to Dijkstra's algorithm, remember that you always pick the next closest vertex not in this blob, okay? When you're done this process, the blob devoured the entire graph, and the edges used to do the devouring, those are the edges that appear in what is called the shortest path tree. And specifically, you could stop this process. If you're just looking for a path T, you could stop this process as soon as you reach T. So hopefully that's clear, everybody. So this is a very simple way you could calculate a shortest path, assuming that if ever you need to travel, you're traveling, either you stay put or you can go forward. So in graph theoretic terms, as long as the edge weights are what we call non-negative, as we have here, you can use this algorithm to compute the shortest path between 2 vertices like this. So I give you 2 vertices. I can use Dijkstra's algorithm to compute a shortest path. But I must stress that once you get what is called the shortest path tree, it's only from the one you start at to every other vertex, not just any pair, okay? So this is just a helpful tool for us, because some of the algorithms I'm going to show you here use Dijkstra, like you can use Dijkstra's algorithm as long as you have some way of computing a shortest ST path. Okay, so now what we're going to do is we're going to take our haunted escape and we're going to use graph theory to now formulate our problem, okay? You're going to see very quickly there's going to be some interesting twist to this if you've never heard of what is called an online problem before. And that's going to be the thing that makes this problem a lot more fascinating than just simply computing a shortest ST path. So what I'm going to do is I'm going to formalize this problem. So remember, we have our traveler. We have this idea of having a graph that we can translate it into. So we're going to imagine we're given. So we're given an undirected graph, undirected weighted graph. That's rather important here. Weighted graph G is equal to VE. With start and end vertices, S and T, which are going to be among the vertices. And in addition, so far this sounds about right, right? The map corresponds to a graph, right? A weighted graph. Yes, Miss Kitty, I know. And in addition, there are edges of E, capital E. Remember, that's the set of edges for our graph. There's going to be some edges that are going to be designated trap edges. So they're going to be called, we're going to call them trap edges. In the literature, they're often called block edges, or they're blockages. So trap edges, which cannot be traversed over. So it means that the traveler can't go past the trap, okay? It can go through another way through, but it cannot cross over a trap. Remember, we don't want to be getting stuck somewhere, kind of like Miss Kitty was earlier. Which cannot be traversed over. So what's the goal? We're going to try to compute, our goal is to try to compute a shortest ST path. So we're going to try to compute a shortest ST path, right? But there's a bit of a catch to this, right? Now, if I knew where all of the trap edges are, does anybody have any suggestions now, given that we talked about Dijkstra's algorithm here? Any suggestions now if, and I mentioned this earlier, that it wouldn't make it much of a difference if we talked about Dijkstra when we talk about no traps versus their knowing all the traps where they are. Could somebody point out or suggest to me how if I knew where all these trap edges were, so imagine, remember, we have an undirected weighted graph as part of the input. We know S and T, that's part of the input. Also, these trap edges, they are technically part of the input with something that we know, like it's part of the problem's formulation. We're going to see that the wrinkle I threw in that we don't know about where the traps are is going to make a big difference. But if you knew where all the traps were, does anyone have any ideas of how we can compute the shortest ST path? And I must stress that we don't have to try it, we can actually achieve it. Well, I'll give you a suggestion where we can go with this. Okay, we know how to compute a shortest ST path. So assuming a path from S to T exists, all I have to do is get rid of all of those edges that are trap edges. Just ignore them. Just straight up ignore them. And then compute a shortest ST path with Dijkstra's algorithm. So you can either explicitly remove them, you could label them, for example. That's another thing you can do. In fact, in my notes, I give a suggestion for how you might go about that. And of course, if you knew where all these trap edges were, you could compute a shortest ST path, assuming that there exists a path from S to T. So there's nothing special going on there. You know how to exactly solve that using what we just talked about over here. You can also do that efficiently as well. But here's the wrinkle. So we will consider an online variant. So I'll explain what online means. It doesn't mean the internet. It means, you're going to see what I mean in a moment. We'll consider an online variant. So that's what our problem actually is. It's actually an online problem. Let me just fix that. The microwave sort of melted the online. Don't put the internet too close to your microwave, okay, everybody? So watch this. So now if we knew where all the trap edges were, we could use Dijkstra's algorithm. However, suppose that you only, as we talked about earlier, as per the rules of how we could escape this haunted house, remember my low budget haunted house? Remember, when I get to a room, the traps trigger on the adjacent rooms, on the passages that connect them, right? Well, we're going to have the same thing happen here. So what's going to happen is this information here about the trap edges is not going to be known to us at the start. So it means that the algorithm will learn more about where these trap edges are as it executes. Or in other words, the traveler will employ what we call a policy to decide how to get out of the haunted house, but discovers these trap edges as they are encountered, just like in our scenario. So notice that this what we call an online problem. Online simply means that instead of it being what we call an offline problem where you know all of the problem's input, so our problem instance's input, and an online problem, there might be some setting or part of the problem's input that is not known to you and it is provided to you as the algorithm executes. So in this case, what's going to happen is these trap edges are only going to be known to us until we touch one of the two endpoints. So the traveler reaches one of the endpoints of an edge. So it touches one of them. Just like when I get to a room, it triggers my low budget traps, okay? So you're not going to jump right in like Miss Kitty was earlier. So here's the catch with this online variant. So trap edges are not known in advance. So they are learned when the traveler reaches an endpoint of a trap edge. So this is exactly the scenario I just described over here with our haunted house. Now, actually, is it really exactly? There is one other wrinkle that I didn't tell you about. Remember, I am the estate. I am in charge of the estate, and remember, I told you that I told the traveler, I told you guys about. I told you something, right? What about the traps? Did I tell you? I told you that there's at most k of them, and k is some positive integer. And I must stress that I'm going to assume it's a positive integer. If it's 0, then we get exactly the original problem we talked about over there, where we had no traps at all. You could just use Dijkstra's. So I'm going to assume there's at least one trap. However, all of the things I'm going to describe to you, it doesn't matter if there's no traps or there are traps. So you might say, Dan, what is this about? So I just want to mention before I give you the name of this problem, it's a really nice classic problem in online algorithms, but I need to give you some assumptions I'm going to make. Many of these you don't necessarily need, but it makes it easier for us to talk about. So I'm going to get rid of the haunted house map, just so I can write this down here. So we're going to have some assumptions, just going to make it easier for me to communicate these ideas to you. But with some very simple adjustments, you can easily adjust it as you wish. It's just that it gets harder to define things for you. So the first thing is that I'm not terribly cruel to you. And remember, you're given the undirected weighted graph, right? So the traveler knows the input graph, right? That's an important assumption. But not where the traps are. So remember, the traveler will reveal a trap once it reaches one of its endpoints. So we won't know it's a trap edge unless the traveler steps on one of the endpoints of the edge, okay? So it touches one end of the passage if you want to think about it as the haunted house. That's going to be one assumption. This is not terribly interesting because we just kind of talked about it there. This is an important technical assumption for the existence of a path from S to T, but I'm going to make it a little bit cozier. Is if the trap edges are removed, the graph G remains what we call connected. So this is one term from graph theory that's rather nice. So what I'm saying is there has to exist a path from, if I give you two vertices in the graph, any two in the graph, there has to exist a path that gets me from one vertex to that vertex. That's what connected means. So it has to exist at least one path that's capable of doing that for any pair of vertices that I pluck off, okay? So if I remove the trap edges, it has to be that the graph after I remove them still has to remain such that I can get from any vertex to any other vertex in the graph. So like I said, I'm not terribly cruel, I just very low budget, okay? And again, like I said, I am very low budget. Is once a trap is uncovered, meaning you found it, it is triggered. It is triggered and never reset. So it never resets itself after. Like I told you, I don't have spring-loaded mechanisms on my traps are made out of straws, okay? Miss Kitty was just sitting on it, okay? So you might ask, so let me just summarize this. I'm going to tell you what this problem is, and then I'm going to add the wrinkle that I just mentioned to you into it. So I'm given an undirected weighted graph. I also have trap edges, but I don't know where all the trap edges are. I just know that they exist, but here's some underlying assumptions, of course. We know what the input graph is, however, we don't know where the traps are. If, of course, we remove the trap edges, there still has to exist a path between any two vertices in the graph. And likewise, if the trap is of course triggered by uncovering it, of course, it never resets. I must stress that there's variants of this problem that we're not going to talk about here that actually allow the traps to get reset. But we're not going to talk about those today. What I've described actually to you just now, without giving you the wrinkle that's distinct for our problem, is actually the Canadian traveler problem. This is actually called the Canadian traveler problem. It's named after basically what we have. Remember, we're trying to find the shortest path from where we are to where we want to go. But imagine you're in a blizzard. And the thing is, you know how to get from A to B. But the thing is, you don't know if there's going to be a bunch of snow that comes out and blocks a road until you run into it. And that's where it gets its name from. So just like our traps in our haunted house, in this case, you could think of it as a big snow blizzard where some of the roads get blocked off, but you don't know where they are. So this is what the Canadian traveler problem is. It's a classic problem in online algorithms. For those that are interested in complexity theory, the Canadian traveler problem, it's actually known, and this was proved by Papadimitriou Yannikakis. I always have fun with that name. Those researchers actually proved that it's what we call p-space complete. So I'm not going to define what p-space is. This is mostly for those enthusiasts out there. The Canadian traveler problem is known to be p-space complete in the case that if you wanted to come up with an online algorithm with what is called a bounded competitive ratio, which I'm going to define what that is in a moment. Competitive ratio. So for those that are wondering what the heck a p-space complete is, p-space is the set of all problems for which you can use polynomial amount of space. P-space complete are the ones that are considered the hardest of those, okay? So I'm not going to go too much into that. However, for the Canadian traveler problem, this is something that's known, so it's going to be rather difficult to come up with a nice algorithm that gets you one that's really close to the optimal ST path, okay? Because remember, we don't know where the trap edges are. This is going to be an inherent limitation that we're going to run into when we try to solve this problem. Now, the problem we're actually interested in is what we call the Canadian traveler problem. And in this version, we know there are at most k-traps. So this is for the general, I must stress that this is for the general problem. This is where you don't know what k is. So this is you can think of this as a specialization of that. So we know that there's at most k-traps. We're going to try to use that information to help us to come up with what we call an online algorithm. But to define that for you, I'm going to need some more terminology, okay? So is everybody doing okay so far? So we're going to be trying to solve this Canadian traveler problem as best as we can. So we're going to try to find a shortest ST path. But the thing is, we can't cross over the trap edges, and we don't know about them until we come across them, okay?